So actually, I think I should start the session because maybe some more will join in between. So I welcome on behalf of our institution, that Engineering College Bikaner, a constituent college of Bikaner Technical University, a state government university here in Bikaner, Rajasthan. So I welcome our expert for this session, Dr. Kush Khanna sir, who is joining from California, US, and he is there a senior project engineer in Hitachi Energy, and he has a very wide experience in the field of cyber security and kind of security and privacy in specifically smart cities. He has performed many projects here at India also during his PhD at IIT Delhi. Kush sir, I wish to tell you that almost all of the experts in this FDP are almost from the alumni of IIT Delhi. So you might have seen in the schedule also that we had one session yesterday by Vipul, who is there in MS at IIT Delhi, and another one, Dr. Ansul, has also performed and presented. One another session is also will be taken by Rahul sir, Girja Shankar sir. Nishant has also presented one of the session. So I think I should read out the citation of, I mean, the biography of Kush sir. So I wish to tell you, all the participants, you are all welcome in this session of this last day of this FDP. So, dear participants, our expert for the today's session, Dr. Kush Khanna, is a senior member of IEEE and received his PhD degree in electrical engineering from Indian Institute of Technology, Delhi in 2019. He worked as postdoctoral research associate with the Department of Electrical and Computer Engineering, Iowa State University, ISU, in US, and is a visiting research scholar with Washington State University, Washington, in USA. He is currently working as a senior optimization engineer at Hitachi Energy, Santa Clara, and at US. His research interests include power system analysis and optimization, smart grid cybersecurity, power system resilience, and electricity markets. So this is about the our today's expert, Dr. Kush Khanna sir. So with this, I think without wasting the time, um, I should give my controls to Kush Khanna sir. So please, Khanna sir, you can now present, please.
Thank you, Dr. Ganesh Prajapat. So first of all, I would like to thank you to have me here, giving me this opportunity to present my thoughts on uh, the the important topic on cybersecurity for power systems. Uh, Although I've moved from academic research to corporate research in last few years, but I still try to remain updated, still reading papers on IEEE on this important topic, cybersecurity. So whatever I'm presenting now are my thoughts, basically the work I have done in the last few years on cybersecurity. So let me try
Okay,
to.
sir, I wish to interrupt one more I mean point. Actually, we the participants are from the different background. So, although this is the many of the people are from the power system or renewable energy or from electrical background, but many of the people are also there from the another background like management, maybe from another branch of engineering like computer science, or maybe from civil or mechanical. So if it will be better if we can have a generalized kind of presentation. So thank you, sir.
Yeah, so I have slides. I will try to be as uh, generic in my presentation as I can.
Yes,
But
sir. Thank
yeah, again, my slides are still on more on power system optimization and broader realms of cybersecurity and power system. So yeah, I'll try to make my delivery of presentation little bit on the generic side. Yeah. Okay, let me try to share my screen. Okay, first of all, it won't let me share my screen without updating the settings. Okay, so Dr. Ganesh, it seems like the Chrome is requesting me to quit and reopen. So maybe I will lose my connection. So I will try to join again because it is not letting me to share my screen without
Okay,
reopening the
okay, no
browser.
problem. You can rejoin, please.
Yeah, yeah.
So participants, you may be in hurry to reach your offices, maybe because this time is somewhat awkward. So please try to stick there in the session. Actually, the this is because of the time constraint. Dr. Kush has not scheduled it as per his time constraint, so that's why this has been rescheduled. Uh, Kush sir, I'm okay, okay, sir. Actually, you are not audible. Maybe you have muted yourself. We are not able to hear you, although we can see your screen.
Okay, so yeah, just give me,
Yeah,
I just
yeah, yeah,
want to
it's okay
see
now.
what's going
Yeah,
on. Just give me a second.
yeah, sure, sure.
Okay, am I audible now? And can you see my screen fine?
Yeah, sir, it's fine now. You are audible clearly and your screen is also visible.
Okay, so yeah, so I noticed that the topic was slightly different. Dr. Ganesh was introducing me, but yeah, I just something like defense in depth framework systems against cyber induced. It still is in line with per se. So differences in the talk I have presented for this lecture. Yeah, I am the senior optimization at Hitachi Energy USA Inc. Working on power system optimization at Hitachi. Yeah, my PhD long back from IIT Delhi back in 2019 when I was working on security related research on power system, and then at Iowa State University in I was Manima pursue on the broader cybersecurity on. So I will try to provide thoughts on the same topic of this lecture. So let me on a question that how much dependence on IT is boon or bane for power. So this is a thought-provoking question. Why? Because about the benefits of dependence now something which called management, uh, uh, the information technology first place. So the IT basically completely transformed how we operate and things. So can now actively participate in the market. So we have smart appliances that respond to time of use pricing. Have our EVs. Basically, we
Sir,
can.
may I interrupt you? Actually, there is some break in your voice. Maybe there is some connection issue or something like that. Actually, although your voice is clear, but it is breaking sometimes. Anyway, although
Uh,
we're able to hear you, if it
I
is,
am connected to, I think, Wi-Fi here. I'm not sure what is the
yeah,
problem.
yeah, it's okay. All
Yeah,
right, no.
yeah. You know, maybe because the connection may not to support it. I'm not sure, but maybe it is since it is a browser, it is create lag here and there. Anyways, so yeah, when we say is there are uh, many examples. Like you have a smart appliances at your home where you can decide when basically use them. For example, your air conditioners, if it supports uh, real-time price switching on and off. So yeah, those can be benefited from the dependence. Also, have we have predictive analysis. What what we call is when we use IT, we have benefits of some database, and then using all the predictive analysis and automation trained on those data sets, which can make our power more reliable than ever before. And also with the emergence of IT, information technology, and OT, which is operational technology, the legacy software of used by transmission system. So this convergence can also enable restore outages and basically in real time the grid conditions. But it can be bad for the operation of power grid. How you are opening up. So now you have many entry points to target a specific uh, generator, say transmission components, and then have a greater dependency on the data integrity, which was not an issue without IT and OT convergence. And now the risk of cascading failures are all if through the compromised IT path. So if can provide you a schematic of how the transmission and distribution looks center the distribution components via wide area communication network. So this could figure whatever is shown in red, basically the new entry points or entry points for targeting the measurements of cascading failure. So the attacker can trip the relay, the generation end, or the transmit, or in the distributed system by targeting meters control the smart. So we are also opening up the cyber attack penetration points to the power grid. So there can be two parts explain the communication layer to the layer and then to the power system layer. So, for example, an attacker can use it to target a corporate server. So, corporate server is where you have providing updates to the substation device, say the transmission system operators, energy management system. So the attacker can path one by sending, say, email to the IT network, and is do a OT-VPN login from the EMS system. Could install a malware to hijack the human-machine interface, and then using that, it can directly trip signals to the substation information operators or important line that could cause uh, cascading failures in the power system. So, so basically, the path one is how the attacker got access to the application layer, and then it uses the EMS of the EMS system by into the application and then sending signal which looks legitimate from the EMS system to a target substation to trip to have a cascaded outage. It's a basic or simple way how attack possibly happen in the cyber physical system of the smart grid. Solution defense in depth framework. We have something which is really identifying and protecting the assets of the smart grid. So reinforce. So reinforce is nothing but resiliency driven risk assessment and security investment planning. We identify what are the critical the critical substations. We reinforce layers to avoid all the cyber security. Then any system, even though if we keep on adding more and more cybersecurity investment to wrap particular critical, sure that the cybersecurity practices which using in the reinforced system still hack proof. There is still possibility then that the attack can. So then we have to have, we see something, some cyber happening in that critical, we have to have a cyber intrusion slash anomaly detection and kind of health monitoring to monitor whether the advanced persistent or the continuous attack is happening right now, what the methods we can use to hit that attack, or maybe we can recover the system from the attack. So stage is recover. So if the attack has compromised certain assets, to use anomaly mitigation and real-time cyber physical, maybe contingency analysis and redispatch to recover whatever is lost because of cyber attack. So this is kind of a three-layer defense in critical assets, and then we have a react to enable detection and reaction on uh, the cyber attacks happening critical assets. And then if we are not able to save them, we still can recover. This three-layered architecture is called continuous risk assessment or defense in depth framework. So when we talk about reinforcement, we say we are trying to identify certain critical assets in any critical infrastructure, be a new power plant or be it. So risk assessment is basically calculating the threat, vulnerability, and impact of any adverse attack on that particular infrastructure, calculated by the product of threat times vulnerability times impact. So here I will be talking about how these cascade outages can happen via disconnection of substation, and how the cascade via falsified scale measurements, the EMS. So when I was talking about risk, I mentioned a threat, vulnerability, and impact. So going deeper into the vulnerability, likelihood of any negative occurrence that would occur and directly related to how the cybersecurity practices are implemented and managed. So if we higher cybersecurity investments, means we have higher of the critical infrastructure, which will definitely lead to decrease in the assets vulnerability. So more and more cybersecurity practices are incorporated in the critical infrastructure, less likely it will be uh, uh, subject to a successful cyber attack. So vulnerability in that way will be inversely directly proportional. Sorry, vulnerability will be kind of inversely proportional cybersecurity investment. More the cybersecurity. So for this kind of research, we used maturity indicator levels as defined in Department of Energy Cybersecurity Capability Maturity Model, known as C2 and 2 models. So there are three levels in which the maturity of kind. So level 1 is basic cybersecurity readiness. Level 2 is a little bit advanced cybersecurity readiness, and level 3, I think I have. The third one is, yeah, the MIL readiness, which is the top level of the possible cybersecurity practices that can be incorporated within the critical infrastructure. So since this was this kind of a model we tried to use in mathematical model, so we tried to come uh, that could link this maturity indicator levels to the vulnerability via the cybersecurity investment. V here is the vulnerability, and C is basically the investments which we are trying to optimize for best cybersecurity practices that can be included for the power grid framework which we are trying to address here. So C1 is the limit of the maturity indicator level 1, C2 is for maturity indicator level 2, and then C3 is the maximum limit for maturity indicator level 3. So the second part of the risk is to to quantify the impact of the event, which is an attack on. From the power system perspective, the impact can be calculated based on how the system is behaving before and after the attack. So before the attack, the system has certain resiliency score. So what is resilient is basically the ability of power system to come back to its original state after being targeted by any attack, or say any event which is trying to reduce its capability of working in the correct manner. So there is no standard formula for quantifying power system resiliency. If you see 100 papers, uh, power system resiliency, but we can agree on the fact that the basic ability of power system is to supply the demand. So all the resiliency matrices will use the system demand met by the generators as one, the resiliency. So for this, we used delta D for different stages as one of the resiliency metrics. So delta D here is the net demand met by the generators at that particular stage. So R1 is the pre-attack stage. R2 resiliency is the post-attack insecure stage. And stage 3 is post-attack secure stage. So for the audience, I think insecure and secure, if the power system engineers or the electrical engineering background audience can understand what is power system security. The power system should be capable of operating in the same state after losing one critical component, be it a generator or be it a transmission line. So if you have, say, element power grid system, so when we say it is n minus secure, that means if we are losing one of the component of a power system, still we will be able to meet the demand what we had before that particular component was removed. So that is what we called secure state of power system operation. So what is post-attack insecure in this case? So if we lose certain critical components in the power system because of a cyber attack or any extreme event that happened in the power system, the post-attack insecure stage is that lose of one more component can lead to cascading tripping, that the system is will not be able to recover back to its original state. Post-attack is the dispatches are rescheduled in such a way that one system component can still be sufficient to provide the load based on the dispatch schedule that level. So resiliency here I have quantified as the difference between the, for example, the entire area, area 1 and area 2 is the impact of the cyber attack happened on the, so so time is dropped from R1 to R2. We took some corrective actions which increased the resiliency score to R3, and then at T3 entire system is recovered. Is the impact of this cyber attack on power system is the loss of can be quantified as the area 2. So that we are trying to the impact of cyber, which is the risk time times I. So I is the area 1, area 2. Then I think this is going more in the nothing but formulation for minimization. So we are trying to minimize the risk, which is VI is vulnerability times impact. So we are trying to minimize the risk in such a way to have the optimized cybersecurity CI, the objective here. So we do this budget constraint B. So yeah, let me quickly go on to the next slide, which lists on is when we are assuming attacker does not have information about the power, chooses to attack randoms without any motive. Kind of a beginner can say the attacker does what is the most critical power grid, or what is the most line that can be taken out to cause the maximum attack. He doesn't do anything. Just have the EMS system, uh, uh, the communication network. He just tries to attack any substation. So if in that case, the threat on each component is same, because random attack we assign same value to all the assets of, say, M So we assign a threat 1 by m. So basically, we are the threat on all m cyber infrastructure assets, and then trying to minimize the total out critical assets from one based on their vulnerability by the security investment. So then if we have budgeting constraints, like we do not want to over, in that case, the strategy for security investments for critical asset one. So this is the optimizing problem for that. Have no assets that can be cause a wider failures in the power system. This becomes slightly tricky problem. So it min max is no longer the averaging out of all the possible attack. By attack vector, I mean from one you have all the critical that can be targeted. So we are not out the threat on all everything the infrastructure critical assets that can cause impact. So that's why you see organization the investment is the the risk that attacker can pose on the system. You see a two-level optimization. The inner level is the attack where it knows that are the critical infrastructures full on that critical infrastructure. It tries to the most critical one out. It is a maximization problem for the, and then in the outer level, it a minimization problem for risk. Security up cybersecurity investments in such a way it can still try to minimize maximum risk a attacker can put on the critical infrastructures. Is the mathematical model for uh, so so now let me show you uh, simulation of triple E or say PGM5 system. So here we have used to the of these attacks on 5-bus system. So you can see in the figure A, which is the healthy power system, with meeting the total demand of 1,000 megawatt. You see there one on bus, one on bus 3, and one on 4. So the system is working fine. N-1 dispatch, which is capable of meeting the security standards. The attacker the substation 1, which is 1 completely. So the generator 1, 2, and all the transmission lines connected to the generators are out. So all of a sudden, you 210 megawatts of generation. So what will happen? the generation 3 and generation 4, bus number 3 and bus number 4 will try to ramp to meet the demand of them. But the problem with this dispatch is it longer n minus 1 secure. While we lose one more line from the all of it, and it may result in cascading tripping of all transmission lines as well, because flow on those lines may exceed. In the stage 3, or one is the attack stage, is 2 is the post attack stage, which depicted by figure B, and the redispatch, which is the stage 3, is depicted by figure C, where particular substation is already out. We cannot get it back anytime soon. So we try to reduce the load to make the system is now again n minus 1 for the reduced bus system we have. So bus number 1 and generate. So we reduce the demand to make sure that our districts are still n minus 1 compliant. So we have to have a load shedding in this. So these tables show how the resiliency is impacted on the attacks which I have explained in this slide. So in the stage 1, you see, which is the pre-attack or a base case stage, the resiliency score was 928.9. Base, the per unit resiliency is 1. But stage 2, even though we were almost meeting all the load, I think just 40 short of case load, which is 1000. The resiliency score is still pretty bad. No longer minus 1 compliant. Most of the transmission lines are being carrying the load close to their limits. So that reduces the resiliency score significantly, 0.6. Then in the third, now loaded, we are not meeting the good amount of load here, but still resiliency score is slightly increased. If I want to calculate the area, uh, area 1 and area 2, I can use these numbers, different stages, R1, R2, and R3 to calculate those. So this will give me the impact. And then I run the optimization model for a beginner attacker and a seasoned attacker. I have these security invest. If I have a limited budget of say 100 units, I will invest on substation 3 here, because substation 3 taken out is having more drop resiliency score. However, if I use where it can try to maximize the impact of taking certain critical assets based on experience of the grid. So investment strategy. Yeah, again, these simulations were on a bigger system, which is IEEE for bus. So this kind of uh, investment is important. Cyber security strategies should be using in the critical infrastructure. So using those investment strategies, we be buying up more intrusion detection systems. We will be beefing up our network firewalls to make sure that uh, the communication happening between the EMS and SCADA system is secure. There is no illegitimate access to any of the critical components within the EMS system or the SCADA system. Scanning, and then also the net traffic monitoring to keep a track uh, on from what ports the attacker is trying to inject uh, anomalies within the communication system. We will also try to invest in detection methods. So based on all these tools, what we can come up with is something which I call as substation health index. We use all these tools to monitor the health of substation. If any of uh, these alerts is certain alarm levels, we can say that health of the system is pretty bad and the vulnerability is pretty high. So this health index or the substation health index can also be used to come up with the real-time risk-aware cyber physical contingency analysis and dispatch. So traditionally, we are using only physical contingency analysis. So this physical contingency analysis is something which says that if, say, one transmission line is out because of a fault or some, is the system good enough to handle all the load or not? So, but now, since if we use this substation health index, we can incorporate that to screen the cyber physical contingencies as well, along with the physical contingent. We can also uh, try to come up with the economic dispatch, which is also cyber secure, not only just the physical secure. So this is the proposed optimization formulation that also uses a substation health index to dispatch generation schedules to meet the system demand economically. So these are the few simulations on how uh, the cyber health uh, index, or say the vulnerability index, is used. For example, the first graph shows that the system, the substation health for substation 1 is reducing significantly. So by 1, it means that it is 100% compromised. By 0, it means it is not even compromised at all. So we gradually, as we reach to certain level, gradually decreasing the generation at bus number 1. Why? Because there is a persistent threat. The substation 1, we don't want the generators in the substation 1 to generate more power. We don't want to be dependent on, decrease their generation and ramp up the other other generators at the other buses to meet the system demand. So this is how uh, the risk-aware security constrained economic dispatch may work if we include the substation health index within the formulation. So the problem one was on how the cybersecurity can help in uh, in strategizing patch if we invest heavily in health monitoring schemes for cyber health monitoring substation and critical components of the power system. However, the attacks can also be uh, uh, happen in the EMS system, which are not that uh, uh, critical in that sense. Like the attacker is not trying to take out certain components directly. What attacker is trying to do is just to manipulate the data uh, which is used for uh, energy management system. So the SCADA measurements can be manipulated in real time, and how these manipulated measurements can lead to incorrect dispatches, which can further lead to cascading outages. So this attack is more stealthy. It is not taking out transmission lines or generators directly, but it is modifying the measurements which are used to schedule these generators and transmission line flows in such a way that over the period of time, these measurements would lead to incorrect dispatches in such a way that those dispatches are no longer N-1s compliant. And if are are making the dispatches not N-1 compliant, that means loss of one longer secure. If we take one critical component out now, we can have a cascading outages in grid. So again, this is more optimization heavy. I'll try to skip these. Yeah, so this is how the measurements can be modified. So for example, on the left side, you see a healthy system, um, a 3-bus. So you have a transmission line limit of 500 megawatt on the transmission line between bus 1 and bus 2, and then 300 megawatt each for the transmission line between bus 1 and bus 3 and bus 2, bus 3 respectively. So these dispatches, what you see in the left figure, the first single shows the total load 50 meg 850 is the generation. A lossless system, loss is, in that case you see flows are pretty easy, 150 and 100, very under limit transmission. So on the 500 megawatt, 150 megawatt of flow is, if fault or some cyber attack line between bus 1 and bus out, we can meet the input of uh, megawatt without to reach the generators, because the line number, the line between 1 and 2 can 100 megawatts. So all megawatt of flow can be the load at bus number 3 and that to load at bus. However, if these mesh in such a way, you see the tweaked measurements uh, in red there. So signal is that which is the power going on, which is not economic anymore. So the redispatch these to be 35 instead of 400 at, and then 465 at bus number 1. This patch is no longer N-1. It looks N-1 system because the measurements what the system operator is receiving are for instead of 150 megawatt, see 65 megawatt of number one. Instead of 450 megawatt at bus number two, it's 41 megawatt of load number two. So it sees that the dispatch was current 50 and 400 and bus number two is not economic. So the economic dispatch, uh, these generations can 65 and 385. So it that the redispatch is very 450 now it is just 65, right? But that 15 megawatt is good enough to cause over transmission line and three. So if some reason transmission line one and two is then the trans bus one and three will be overloaded 15 megawatt, and that 15 megawatt is the over relay tripping between these tripping for this particular trans line as well. You lose the entire 465 megawatt generator. Now 150 one is not, it still can be served, but 5 generation at bus number 2 is not sufficient demand of 4 250 megawatt of power, which is 700 megawatt. So you have a loss of flow, have consumers which are now electricity because of this stage or minus one insecure. This so how to the anomalies, and what we can use statistical methods to come up with the correlation between the measurement reading based on historical data and the number which we are seeing from the EMS. So we try to or find the correlation between the true the to to see whether this particular data is uh, have, falsified or not. We can also learning based anomaly detection module use the data to train itself uh, for different and come up with a trained model that can predict correct measurements based on real time. Some of the real time measurements are like, so we can use either based anomaly detection module or say statistic anomaly detection. Then we can come up with physical anomaly mitigation system. Uh, it it use certain secure measurements because PMU measure use a different protocol, is a newer technology, and since we do not have any PMU measurements for all the substances, so we can uh, encrypt communication channel in such a way that the measurement cannot be hacked or um, changed or spoofed by an attack. These secure MU measurements to the state of power, current state of power, and these secured PMs to predict the other measurements, which still can be spoofed. The difference between the predicted SCADA measurements and what we are seeing from the mission, uh, and try to find out the, and if the difference is greater than the threshold, these particular measurements already perturbed, and we use the train SCADA measurements to keep energy management system healthy. Could be the answer to all these false data attacks, or the data which we have from the historical uh, uh, measurements data can also be used for statistical correlation between the correct data and the anomalous data. So this is be the third stage, how to recover from the cyber attack. The key takeaways of this session is we need to from domain specific point cyber physical assessment. So for now, last 4 or 5 decades, we are specifically uh, uh, deciding power system may behave under extreme events, but now we shift from the power system domain to say a physical domain to understand the smart grid better, to make sure that uh, we can save the future smart the cyber attacks. Also need uh, aware cyber physical contingency planning. Physical contingency planning, which deals with the physical loss of transmission line because of a fault or factors, is now towards the contingency because of cyber-induced events. So we need to more. It's a high time we update our legacy software to include cyber physical contingency as well. Then future, what do we need? Do we need a market reforms and to include cyber induced contingency in the economic dispatch? We don't right now. Because if you keep on more trains to the optimization problem, keep on adding more and more security feature economic dispatch problem, it will become more and more expensive for the consumers. Previously, you the system to be n minus unsecure. You want to make the power reliable of any environment. You have sufficient reserves in your power system to the grid up and running and to demands of the consumers. Now, to go one step ahead, what if weather related or fault related event? It is a induced event. Now you would like to have more to counter any cyber induced contingents in the power grid. Reserves are not free reserves, right? It is costly. It is uh, uh, what are different types of stations. It could be a multi-fuel generation station, which is providing a reserve, or it could be or solar, which is providing a reserve. But wind and solars can be a reserve only when there is a sufficient wind or solar. It is highly intermittent. For reserve planning, usually we multi-fuel generator system, because contingency we need those reserves. We cannot be relying on something intermittent in nature as wind or solar. So fuel generators will be more expensive. And if we add that to the operation of a power grid, uh, the cost per megawatt will become costly for the consumers. So to in these cyber physical contingencies in the economic patch, that is probably the answer future to make the power system more reliable in the growing uh, world. interconnected systems. Uh, yeah, so that's all I have for the lecture today. I hope it makes some sense to all the audience from different backgrounds. If you have any questions, you can ask now, or would like to send me an email. Questions you have, you can send me an email on my email shown on the slide. Any open for questions for now? You know.
Yes, thank you, Kush sir. So your presentation was really wonderful. Participants, if any of you have any kind of query, any kind of question, they can directly ask to sir. He's live. Uh, Although your presentation was really wonderful, actually it has full of information, and I'm sure the participants who are working in this area will definitely get benefited out of this presentation. Actually, in general, the presentation in out of the presentation, everything has been told at the stage of slide second only, because we, as a general people who are not in working in the cyber security area, may be able to understand that in case of finance, we are able to understand what exactly the impact of cyber crime will be there. In many of the participants may have heard or may have been affected by some cyber way in their finance, but since it is equally important in the case of power systems also. So Kusar, is I have one general query, although is it is equally important in the case of our Indian grid and Indian power transmission and distribution systems?
Yes, and I think Indian power system is growing, and uh, I remember with the POSOCO engineers when I was at IIT Delhi, and they were saying that our state estimation system is still kind of, how should I put it? We are we will not be having any cyber related issues. Why? Because our IT system and our OT completely different. There is no interlink between those two. And also, even if we see a wrong measurement, transmission lines are so underloaded that we may not be the cascading outages in future. But now, I believe in POSOCO is also trying to get more and more digital components in power grid infrastructure, and they are coming up with the real time uh, economic dispatch, real time contingency analysis, and then state estimation is also now being integrated into their operation. So yeah, with all these advancements, definitely cybersecurity pose a big issue to Indian power grid as well.
Yes, sir. Yes, thank you. So actually, the estimation is one of the important thing also. Since, as I understand that the cyber way, I mean, the cyber attacks could only be handled through some good data. Actually, this only depends on the availability of the data. And sometimes, if these data are not available, then we need to estimate these data. So the estimator, which actually be present for extracting the information, that must also be very good in the science, right?
Yes, that's correct. So
Exactly.
the state estimation from the power system perspective is as a part of energy management system. It takes all the measurements data from the ICCP protocol, or say the substation, inherently was secure. Why? Because there is no way of any intrusion going inside. that communication protocol. But now, if the EMS system is also connected with OT, because uh, EMS system is also connected with IT. In that case, yes, there could be a data manipulation happening. So then the quality of data which the state estimation is receiving may not be correct. And then there will be a wrong estimated states at the power system side, which could lead to further issues in the power system. Yeah, that's correct.
Okay, great. Thank you. So actually, I have also been worked with one of the estimation, state estimation technique in my PhD, and also doing one more work on it. That was about the uncentered Kalman filter, which actually I have used for the estimation of some internal states of the wind power generating system, which actually being fed to the grid. So although that has I think that has already been implemented in practical by Hydro-Quebec Institute, wherein Professor Innocent Kamwa has implemented this. So I think you have also heard about that. So
Yeah.
actually, I mean that if I could be able to incorporate this cyber security in estimation kind of techniques, so it could be happen, right?
Yes, it depends on what kind of states you are trying to estimate for your wind turbine, right? So I think those are the internal states of the wind turbine generator, which is not directly affected by the outside noise. By outside noise is what I mean is you are having the measurements directly from the wind turbine generator to come up with the internal states, right? And then using your Kalman filter to come up with the activating signals, or say PI controller to come up with the logic to inject some reference or corrective signals to the wind turbine generator, right? So those are the internal states which you are trying to directly read from the measurements which is there in your right in front of your wind turbine generator, which is still a local measurement. This problem of cybersecurity is prevalent. You use measurements from the remote devices which are far from the the control system. So if the control system and the measurement devices are both local, you have a hard wire between the measurements and the control system, right? But if the control system is far from the measurement devices in the first place, then within the communication medium, there can be a cyber attack that can modify those measurements while they were being transmitted to the control system. So yes, so control, if your controller for the wind farm is outside of the wind farm, far from are trying to get all the measurements for your Kalman filter via some communication medium that can be hacked, yes, you have to incorporate your cybersecurity there as well. If not, then yes, you are cyber secure already, because there is no way anyone can modify those measurements if they're all done locally.
Yes, yes.
Yeah.
So I remember one more I mean work on it actually inside the unscented Kalman filter in the steps of there is in between an intermediate stage where one can extract that if there is any malicious data or kind of unusual or outright data, then there is one kind of bad detection may be provided there. Uh, I
Yeah.
I I know that one of the work being presented by Professor Pratyasa, who is also from IIT Delhi, PhD from IIT Delhi,
Yeah.
and he is now in IIT Dharwad. He has also done some kind of that work in uncertain Kalman filter. He has extracted some state in between, or I think one index which is actually in the process of that uncertain Kalman filter, and ultimately, if it goes some value from its given bound, then it actually shows that there is kind of cyber attack is there. So that exactly reflecting the same thing. This is what
Yeah.
I am getting out of it. Yes, yes,
Yes,
exactly. Thank
yes. So for power
ठीक है, तो
system
वेगळे
information
लक्षात
also
ये भी
we
लपेटे में ये तो इनके जैसे
for power system, I'm sorry, someone is asking a question.
Is there anyone wish to ask something? Okay, perhaps it may be because of
Okay.
some.
Yeah, so power system traditionally also have a bad data detection algorithm which tries to identify some telemetry errors in in the state measurements. However, when we talk about false data injection attacks, we also uh, say that these measurements are also uh, function power system uh, impedances. In the simple terms, I can say and satisfy Kirchhoff's Kirchhoff voltage law directly. So if these satisfy all these laws of physics of the power system, then no traditional bad data algorithm can detect them as bad. So these spoofed measurements are intelligently crafted, and they are so nicely crafted that they can project a completely different state of a power system to the system operator. So that is why these are very dangerous. They bypass all the bad data detection algorithms, and it leads to a incorrect dispatch to correct the power system state, and that incorrect dispatch could be could be the cause of cascading failures in future. Yeah.
Yes, sir. Yes. So thank you for your insightful presentation. If any of the participants, if they wish to ask something, you can put your question. Otherwise, we are getting, we are just closing this session. Is there any participants wish to ask something? If there is any question from the chat, we can also see there. Kush sir, are you able to see the chat? I think there is nothing there in the chat also. So I think we
Okay,
should.
let me see. I can see the chat, but there is no.
Okay, all right. So thank you once again, Dr. Kush sir. He has joined from California, US, and we are very much privileged to have you in this wonderful session today on cybersecurity and privacy in smart cities. So the presentation was really wonderful, and I personally have understood everything, although not in deep, but what exactly the importance of cybersecurity in the in the smart cities that has been delivered by you very uh, great manner. So once again, I am very much thankful to our expert for this session and also participants to listening patiently. So thank you, Kush sir. Thank you very much. Uh, Although this was the, I think there is the timing constant is also there. What about the time, sir? There at US, California.
Yeah, yeah. Currently, it is close in the evening here.
Oh, so it was a, it
It,
was very tired day for you because you are coming from your office and then just this is the
no, it
time for your rest.
was
So
a
you have,
holiday, but I was
okay, okay.
away. So that's okay.
Okay, okay, all right. So thank you, sir. So in future also we will be there in touch and we will do some future collaborations also. So thank you very
Yeah,
much.
definitely.
So for further, although you have told that you will not be able to get the honorarium out of the AICT, but if there is any kind of possibility regarding the honorarium, then we can have, since as I already told that there is one provision of giving the honorarium from AICT side. So we will be honored if you have that honorarium in anyhow, anyway, and otherwise we will be in connect in future also.
Yeah, no, uh, Ganesh sir. So yeah, that's completely fine. I understand it. So yeah, thank you again for having me
Okay.
here. Me up presents
Yes,
my
thank
thoughts.
you very much.
Yeah,
Okay, thank you very
yeah,
much. You can now leave the meeting, please.
yeah, yeah. Thank you.
Thank you very much. So, participants, there is one important announcement for you. Actually, we have, since this is the last day of this FDP, and we have two more session and as well as valedictory session and quiz session also. Uh, so, I have already sent you one mail, and therein the timing of the quiz is mentioned. The quiz will be live, remain live in between the 7:30 to 6:30 to 7:30. So I'll post although there on mail, and since you need to be present there in the meeting, so that's why I'll post the link of that quiz in the this WebEx meet only. So you must be present during the attempting of this quiz in the WebEx meet. So although I'll post the update on it in the WhatsApp group also, but this is the important announcement that you should attempt the quiz, because your certification will only be secured in the case of attending that quiz. So I once again thank you all the participants for attending and the session very patiently and listening to our expert. Thank you. We will meeting at afternoon session. It is about 3:30 afternoon. So thank you. Thank you once again.
Thank you, sir.